Hi there, and welcome to this lesson. In this lesson, we'll be learning thermal expansion, okay, and we'll be learning about thermal expansion in liquids. Now, the last time we learned about thermal expansion in solids, and this time we'll be learning thermal expansion in liquids. Now, thermal expansion in liquids is very, very interesting, and we will find out all about it shortly. But at this time, I'd remind you at any point in the lesson, anything you don't understand, be sure to get across to your tutor, who would be more than happy to help. And yes, let's jump right into the lesson. So, thermal expansion in liquids. Now, liquids typically expand more than solids, okay, because the intermolecular forces in liquids are much weaker. Now, if you recall, I explained to you how expansion works. Basically, when you heat a body, the molecules of that body, the particles in that body tend to move about more vigorously, and this because of this vigorous movement, you generally have a the tend to move across a larger space, and basically you have expansion as a result. For liquids, is a lot more the motion is even more vigorous, okay, because generally the intermolecular forces, the forces holding the molecules of a liquid, are a lot smaller, a lot weaker than the ones for a solid. Basically, which should make some sense to you. And basically, when you apply heat to a liquid, it moves even more, the molecules tend to move even more vigorously than you have in a solid. And basically, liquids expand with volume. Okay, you can't find the length of a liquid or the area of a liquid. You can only find the volume of a liquid. So liquids expand with volume. So we have cubic expansion, and basically you have the exact same formula, the same thing applies. The cubic expansivity of a liquid is the change in the volume of the liquid divided by the volume of the liquid, and the change in the temperature of the liquid when it's heated. Now, basically V1 initial volume, V2 final volume, theta1 initial temperature, and theta2 final temperature. Now, there's something very interesting about the expansion of liquids, and this comes as a result of the fact that liquids are always contained in containers. Okay, so liquid are always contained in containers. Now, here's what happens when you have a liquid in a container, okay, and you heat that liquid up in that container, the liquid would expand, okay, but then the expansion that you would perceive will not be the actual expansion of that liquid. And the reason for this, the reason this is this basically, the container will expand as well. Okay, for example, let's say you have a liquid in a calibrated beaker, okay, and then you start to heat that liquid up to basically identify the rise, how much the liquid will rise in the beaker. Now the thing is, when you observe that rise in the beaker, it would not be the exact value of the expansion because the beaker itself would expand as well. So there is a slight difference in the expansivity of a liquid when it's placed, when you're heating it in an expandable solid. And that is where real and apparent expansivity come. Well, that's where the whole principle comes from. Basically, the real expansivity of a liquid is the actual expansivity of that liquid, okay? What's actually happening. But the apparent expansivity is what you observe, okay? And that observation is there's a difference in what's observed compared to what's actually happening as a result of the fact that the container expands as well. So liquids are always contained in containers. When subject to heat, the containers expand alongside the liquid that alongside the liquid that they contain. Now, as a result, there is a difference in the observed and measured expansion from the measured, observed expansion, the apparent expansion from the actual expansion of the liquid. And basically, the observed and measured expansion is called apparent expansion, whilst the actual expansion is called real expansion. And then real expansivity is the standard expansivity increase in volume per unit rise in temperature. So that's exactly what's happening to the liquid. And then basically you have that, the same formula. But then for apparent expansivity, we have the apparent expansivity is the increase in volume per unit rise in temperature when the liquid is heated in an expandable container. Okay, so it's the visible change, the observed change in the volume of that liquid, okay, as opposed to what's actually happening. Like I explained to you, basically when you're heating a liquid in a container, there is a difference between what you see and what's actually happening because the container is expanding as well. So the change that you see is apparent, becomes from the apparent expansivity, while the change that's actually happening is from real expansivity. And basically you have observed change in volume divided by the initial volume, and then you have the change in temperature. And something very important you need to know is that the real expansivity equals the sum of the apparent expansivity plus the expansivity of the container. So if you're given the real expansivity of a liquid, and you're given the expansivity of the solid container, to find the expansivity that will give you that observed expansion, you just subtract the expansivity of the container from the real expansivity of the liquid. And yeah, finally, one thing we need to talk about is very important. Change in mass. Okay, we often apply this. Okay, when you have a liquid in a container, in an expandable container, and that liquid is put, basically the liquid is fills the container up until the brim. Okay, now when you heat this liquid, some of the liquid will move out of the container, and you're often required to find the mass of the liquid that be left in the container. But then what it is given that the density of the liquid is constant, okay, you have that with the density of the liquid constant, you have that the apparent expansivity equals the change in mass. Just basically the same thing with the volume. If as long as the density is constant, the same thing with the volume, that relationship stays for mass. So you have change in mass divided by the initial mass divided by the change in temperature. And yeah, let's go ahead now and solve some examples. Yeah. Example 1, and we have the real expansivity of a liquid is 180 times 10 to the power of minus 6 per Kelvin. If the liquid has a mass of 500 grams and a density of 1.36 times 10 to the power of minus 4 kilogram meter minus 3, okay, kilogram per meter cube, determine the new volume when heated with a temperature rise of 20 degrees Celsius. Okay, so we're given mass and we're given density, okay, and we're told to find new volume. We're given expansivity, we're given the change in temperature. Now, since we're asked to find volume, okay, the first thing we need to do is we need to find the initial volume of this liquid, okay, and to find the volume, we simply divide mass by density, okay. So we're told that our mass is 500 grams and 500 grams is 0.5 kilograms, okay, and our density is 1.36 times 10 to the power of 4 kilogram meter minus 3, okay. And basically when we divide that, we end up with a volume as 3.676 times 10 to the power of minus 5 meters cubed. Okay, now that we have the initial volume, we're going to go ahead now and find the final volume. So we have, there is no expandable container in this case. Basically, all of that is we're negligible. Okay, we're not considering the container at this time. So we're just going to be working with the real expansivity of the liquid. And we have, we're assuming that this liquid is being heated in space. Basically there's no container, but basically let's go ahead and work this. So we have the real expansivity equals this, and we just change that, make v2 subject to formula, and what we have in the end is we have v1 as 3.676 times 10 to the power of minus 5 meters cubed. We have our real expansivity is 180 times 10 to the power of minus 6 per Kelvin, our change in temperature is 20 Kelvin. Okay, it's 20 degrees Celsius, it's 20 Kelvin. Reason for this is it is a change, a difference in temperature. Okay, you're always working temperature in Kelvin. So for example, if you're given 50 degrees Celsius, you have to convert that to Kelvin. I think that would be 323 Kelvin when you add 273. And if you have 0 degrees Celsius, you have to add 273 degrees to give you Kelvin. But when you have a change in temperature, adding 273 degrees to both temperatures and subtracting them at the end will pretty much give you the same answer as just subtracting them as they are. So basically, if you have a change of 20 degrees Celsius, you have a change of 20 Kelvin. And yes, you just go ahead and apply all of that to your formula. You should end up with your new volume as 3.69 times 10 to the power of minus 5 meters cubed. Okay, that's our new volume. Very simple, very straightforward. Another example. Example 2. Okay, now we have a bottle, so we have a container in this case, and we have a bottle that's filled with mercury, 500 grams of mercury, and on heating, its temperature increases by 30 degrees Celsius. Calculate the mass of mercury left in the bottle, given that the real cubic expansivity of mercury is 180 times 10 to the power of minus 6 per Kelvin, and the cubic expansivity of glass is 24 times 10 to the power of minus 6 per Kelvin. Now, we're going to be working with the apparent expansivity here, okay? And we have the real expansivity. We're given the real expansivity. Okay, we're told that this mercury is contained in a bottle. Now, when we apply heat, we change the temperature of this the bottle and the mercury in it from 30 to from let's say 0 degrees Celsius to 30 degrees Celsius. There was a temperature rise of 30 degrees Celsius. Okay, and then there was a real expansion of the mercury, but then there was also expansion of the bottle as well. So we have, and then some of the mercury, because the mercury was filled, so the bottle was filled completely with mercury. Now, some of the mercury escaped from the bottle, okay, was expelled out of the bottle as a result of the expansion. Now, you need to keep in mind that you're going to be talking about the apparent expansion in this case, because like I said, the mercury expands following its real expansivity, but then the bottle expands as well. So the bottle actually creates more room for the mercury. Okay, so there's more mercury. Basically, let's assume the mercury did not expand at all. If the bottle in itself expanded on its own, you'd actually find, if it was completely filled before, you would actually find more space, basically, because the bottle would expand, creating more room for mercury. So if you're going to find the difference in their expansion, okay, you will need to make use of the apparent expansivity. And apparent expansivity is just the real expansivity minus the expansivity of the container. We have real expansivity of the liquid as 180 times 10 to the power of minus 6 Kelvin, and we have the expansivity of the container as 24 times 10 to the power of minus 6 per Kelvin. We just go ahead and find apparent expansivity as 156 times 10 to the power of minus 6 per Kelvin. Okay, now that we have our apparent expansivity, we now need to find how much the how much the how much how much the how much the mercury would expand. Okay, so we have and in this case we're working with mass. Okay, so we're working mass, assuming density remains constant. We have a new mass. Okay, so we have delta M equals M1 apparent expansivity delta theta, okay, and we have our M1 as 0.5 kg, expansivity as 156 times 10 to the power minus 6 per Kelvin, and change in temperature as 30 Kelvin. Now, when we heat the mercury, okay, a bottle that's completely filled with mercury, it will expand, and then there would be little room for the mercury, and some of it would actually have to go out of the bottle, okay. And then that's exactly what we're looking to find now, the change in mass, okay, the increase in mass following the apparent expansivity. And we have that change in mass as 0.5 times 156 times 10 to the power of minus 6 times 30. And we have this as the mass expelled, okay, that extra mass. Basically, when the liquid expands with a completely filled bottle, some of that liquid will actually would be expelled out of the bottle. And it's that change in mass, that increase in mass that we're looking for here. Not necessarily an increase in volume, but some of the mass getting expelled. And some of the volume getting expelled, the mass getting expelled. And what we have is we have this, and to find the mass remaining, Mr, we just subtract the mass expelled from the initial mass. And what we have in the end is we have 497.66 grams. And yeah, that would bring us to the end of this very simple lesson. Okay, if you're going to take anything away from this lesson, you need to be clear how real and apparent expansivity work. Okay, and how real expansivity is apparent expansivity plus the expansivity of the container. And then yeah, you can go ahead now and attend questions on the worksheet. Bye for now.